let's get going. We start chapter 10 today. Yeah. As a whatever you want to call it, we did, I want to say 9% better than we did last test, so that's positive. I had one student go up 20%. They were pretty stoked. So realize that we've got basically 4 tests left. 10, 11, 12 in the final. Okay? I assume you're all still sitting here, which means you all believe you can get a 65% or better test average by the time the year's done. Dude, don't shrug your shoulders at me. I only talked about last Friday how many times?
Yeah, a million.
Whoa, Jed in the back. Iverson, raise your hand. Well, probably not a million, but enough. But I do really like your shirt.
Thank you.
Not that shirt, that shirt. The Def Leppard shirt. Yeah.
You know when the end of the term is?
19th?
That's in like about 2 weeks, right?
It is not. It's 3 Fridays. Why?
You just didn't believe me about the end of the term was.
Yeah, literally. It's. I was shocked. I'm looking at it last night. It's 3 Fridays. Like not this Friday, not next Friday, but the next. So that's the end of 3rd term. Okay, and as it looks right now, we will take this test like the second to last day of the quarter. Probably will not go on this quarter's grade, but we'll see. Okay? Alrighty, so it is 3-2, right? March 2nd? Yeah? Alrighty, and this is 6th period. And this is Chem. 11:10, chapter 10. Day 1. I did share that, so hopefully. Did anybody go through the book and do it yet?
What?
Do the Learn Smart 1?
No, I didn't.
It wasn't. I looked on the actual McMillan.
I know,
and
but
it said without credit, so I didn't.
Yeah, you can go in. You can still do that, and then it'll cycle through.
Okay.
Yeah. I'd forgotten, and clearly no one wanted to do it, because usually someone messaged me and go, hey, you forgot to share the Learn Smarts. But obviously I was there going, yeah, no, I wouldn't do that. Yeah, I ain't stupid. And you're all laughing, so you're all in that boat, right? I see how it is. I remember all that come grade time, an F for you and an F for you. Yeah, jerks. Alrighty. So our objective is going to be able to better understand radiation and radioactive decay. Now, one thing you do need to understand is that there are only 7 sections in this, and we're actually only going to teach 6 of them. So that's only 2 sections a day, so hopefully that will be some time. Before I think about this, I have out of this class alone, I think I am missing 17 labs from this class alone. Now, don't keep your hands. Just don't. Okay. I think I'm missing 17 labs this quarter alone. So out of those 3, you think about it, that's a lot. Especially when that's 20% of your grade. I think I have one student where I'm missing all 3 labs from this quarter. So we need to get these done like ASAP. Okay? Alrighty, now first thing we gotta talk about is we gotta talk about isotopes. Now we have talked about isotopes in the past. Does anybody know what an isotope is? Okay, so it is an element with, what were you saying, Fish?
They have a different number of neutrons.
A different number of neutrons. Okay. So what does that mean?
So on the periodic table, they have a specific amount, the way they're supposed to have generally, but they.
Okay, so that's the average. Okay. So if I have a different number of neutrons, what do I have the same? Yeah, my protons don't what?
Change.
Yeah, your protons don't change. Your electrons don't change. Just your neutrons. Now, the general form of this is this. X, A, Z. This is like the generic version of an isotope, right? The X is where the what goes? That is where the elemental, it's called the symbol. That's where the symbol goes. Okay, what goes up here at Z? Not weight, we use
Atomic mass.
mass, but that's not what goes there. Up here is the mass. Up here is the mass number, and the mass number is the what? Anybody remember? Say it out loud, Richards. That is the protons plus the neutrons. Okay, the bottom number is the anybody remember what it was called? It's the atomic number. Atomic number, and it is simply the number of what? Number of protons. Okay. So what they'll do is they'll say, and they'll write this two ways. Like, let's say I gave you something. Let's just pick an element out. So let's say I used, I don't know. Let's say I used, here we go. Let's say I went uranium, and we said that this is uranium-235, right? What is my subscript down here going to be for U-235?
92.
It's going to be 92. And no matter what, if it's uranium, is that number ever going to change? It's never going to change, ever. Okay? Now, this is one way to write uranium-235. Another way is they will write that in a word form, and it'll go uranium. Does anybody remember how we wrote this? It's been a long time ago, by the way. Yep, uranium-235. We did this back in like chapter, I don't know, 3 or 4. I'm sure none of you remember that far away besides Garrett, but you all looked at me like I was an idiot. But whatever, okay? Either way, these mean the same thing. And they will expect you to go from this form to this form, okay? Now, for the most part, isotopes behave the same. The only thing that changes is their what? Yeah, the only thing that changes is their mass. Okay? Now, they are going to do, I don't know, they're going to do some pretty easy things. It's like, let's say I gave you, I don't know, let's say I gave you plutonium. Plutonium-240. And I wanted you to write that as a symbol. Okay? This is written kind of out as a word, and I wanted you to convert that into a symbol. Well, the first thing I've got to do is I've got to know what? I got to know the symbol for plutonium, right? Which I'm surprised they haven't changed the name of. Right? Didn't they declassify plutonium as a planet like 10 years ago, right? So you said it's what? PU. Okay, PU. Then what goes where? How would I write that? So 240 is my subscript or superscript? Superscript is 240. At the bottom I'm going to have 94, right? Then they'll start asking you questions about this. They will say how? Yeah, many neutrons are present or something like that. Okay? Well, how do I figure that out? Yeah, I'm going to take 240 and I'm subtract off 94, and that's going to give me how many? 146 neutrons. Something like that. Okay? Pretty simple, and there are a couple of those type of questions on the test. Okay? Now, radioactive. Let's start with radioactivity. Anybody know what radioactivity means or what it is?
Giving off particles.
Okay, it can give off particles. Not all radioactivity is a particle, though. Okay, radioactivity is the radiation emitted. Emitted means what? Given off, right? Emitted spontaneously, which means what? But it just happens spontaneously by an unstable radioactive isotope. Okay? Now, if something is radioactive, okay, if I said radio, and it's funny because I look at that definition, I'm like, man, there's a whole lot of words there that your average human probably doesn't know what they mean, right? So if I use the term radioactive, what does that mean? Anybody? If something is radioactive, that means it gives off radiation. Okay, now the problem with that is that radiation in and of itself is kind of a unknown term to most people, right? Now, what we're going to do is we're going to talk about the different types of radiation. Okay, now we're going to focus on 4. That doesn't mean there's only 4. That simply means what we're going to focus on are 4 types of radiation. Okay. Now, the first type of radiation is what is known as an alpha particle. An alpha particle. Okay, you got an alpha particle. Now, an alpha particle is a high energy particle that contains 2 protons and 2 neutrons. Okay? Now, an alpha particle is written 2 ways. This is like the definition of an alpha particle. The symbol for an alpha particle, somebody just got a message, is this or this. Okay? Now, either symbol is acceptable, and they will use them interchangeably. Sometimes I'll write it like this, sometimes I'll write it like that. Doesn't matter. Okay? Now, with that, though, you need to understand is it has a charge of +2 and a mass of 4. Obviously, it's got a charge of +2 because it's got 2 what? 2 protons, which means it probably doesn't have any what? Electrons. Because if it had any electrons, they would do what to the charge? It'd cancel it out, right? And obviously it has a mass of 4 because my superscript, which is where the mass number goes, it has a 4. Okay? That is a alpha particle. Alrighty, from an alpha particle, you need to know what a beta particle is. A beta particle, okay, is basically a high energy electron. Okay? Now, besides the fact that it's got an immense amount of energy, being an electron means what of its mass? And we know how much mass an electron has?
Not a lot.
Pretty much none, right? So it's kind of interesting that beta particles are a form of radiation. And last time I checked, radiation is bad, right? I mean, you see, like, we've all seen Godzilla, right? No, Iverson, you've never seen Godzilla? Wow. Well, anyway, you talk about Chernobyl. Does anybody know the word Chernobyl? Raise your hand if you've heard. No, actually know what it means. Oh my hell. Really? Where did you learn about Chernobyl, Richards?
The news so many years ago.
Okay, what about you?
Just heard about it.
Heard about it? What about you two? Just heard about it?
Or the history.
Wow.
Show about it.
I'm going to have to dig something out on Chernobyl. Chernobyl was the single greatest nuclear reactor accident in the world. 80s? Yeah, it was the 80s. Yeah. I was alive. I remember. It was a big deal. Yeah, it's still a big deal. Because they claim that they built a nuclear reactor, and then they built a city around it for those people to work at, because it was the next, nuclear energy was the future. And it still might be. But they had what's called a meltdown. There's a great YouTube video on the meltdown. Killed a lot of people. Irradiated a bunch of things. Birth defects were high. I mean, radiation's bad in that sense. Yes?
Is it like that one town that's deserted and is not, like, you can't go into that?
Okay, when you say is it like that one town, it is that one town. Yeah, it's called Pripyat. It's in the Ukraine, Russia back then. And yeah, it is still, the nuclear core melted into the basement of the facility, and it's still there. It's called the Elephant's Foot. And if you were to stand next to that to this day, 35, 40 years later, in a couple of days, you're, let me think, dead. Yeah, it's crazy. Crazy. Yeah, wow. Might have to find something on that.
There's a show about it on Hulu.
Oh, there is?
It's called Chernobyl.
Oh, it is? Oh, well, there's used to be some really good, like a guy, like when it first happened, they claimed it would never be inhabitable again, right? But to this day, you can see that it's like, I don't know, maybe 10, 15 years ago, there was this TV series called Life After People. Anybody ever see that? No? Well, they used to use CGI to show what would happen if we didn't exist and how the earth basically reclaims things, right? Well, this city is being reclaimed because it's literally out in the middle of a Russian forest, Siberian forest, I guess, right? And you can literally see the forest reclaiming it. And in one shot, and this has been a few years ago, so I don't know if it exists, there's a parking structure like the one down at the mall, big concrete one. And there is literally a tree growing right out of the top of it. Right growing out of the concrete. It's way cool. Because nature finds a way. You know what I mean? And so even though, it's still radioactive and people live by it now. You can't live there yet. They claim you never will, but you know how people are, right? They don't listen. So that's my students. I had a 7 a.m. study session that nobody came to. Oh, burn. Geddes is over there going, yeah, I got you. But anyway, the forest is reclaiming. I'll see if I can find something short we can watch. Okay, so beta particle. And a beta particle usually has a symbol of beta that looks like this, which is why I always write my B for beta particle like that, right? Or they have this particle, E0, -1. Okay, now again, my superscript is its what? Mass. Subscript is its, in this sense, it's going to be its charge. Okay, it's a -1 because it doesn't have any protons, right? Okay. And that's beta particle. Okay, now from there, we need to know what a positron is. Okay, a positron. A positron, sometimes referred to as an antiparticle, and we're in reality, we're not going to get into like antimatter and stuff like that. Okay. And it's let me rephrase it. It's an antiparticle of a beta. Antiparticle of a beta. Okay. And that is because their charges are different. Okay? But their masses the same. So a positron can be symbolized as a beta positive, okay, or a basically something that most people don't think exists is a positively charged electron, okay, which is why they call it a positron, okay, positron, okay. Alrighty, and then the last, because I said we were going to focus on 4. The last, does anybody know what the last type is? Nobody? Is a gamma ray. I'm sure we've all heard of gamma rays, right? A gamma ray is high energy radiation released from a radioactive nucleus. Now, the difference between all those other 3 and this one is that this one is a what? It's a ray and not a particle. Okay, which means this one has no what? Has no mass, has no charge. Okay? And the symbol is this funky looking, Y looking thing. That's a symbol for a gamma ray. Okay? Now, a lot of times, gamma ray accompanies other kinds of radiation. Okay? Because if not, you don't even know. It's like something could be giving off gamma rays and you wouldn't know. Because its mass or its charge never changes. Okay? Now, why that's important is because we're going to get into nuclear reactions. Okay? Now, what they're going to do is they're going to say, given uranium-235 that decays by, I don't know, let's say 2 alpha emission, write a reaction. Okay? Well, I'm going to start with U-235. Okay, well, what's the symbol for U-235 going to be? I'm going to have U-235, and what did we say uranium was? 92, right? Now, it decays by 2 alpha emission. When they use the term emit, it is being what? Given off, right? Which is going to make it a what? Anybody know? I'm writing a reaction here. Reaction's got some, every reaction's got some reactants and some products, right? If I'm emitting it, it's going to make it a, well, it is, but it's going to make this a reactant or a product. It's going to make it a product, right? So I'm going to start with U-235. I'm going to end through 2 alpha emission. Okay? Now, I wouldn't write it as 2 alpha. Okay, I would write this as 2 what? Yeah, I would write it as He4 and 2. Plus, and then there's got to be something new there. And that's what happens through radioactivity. I have one element that changes into something else. It's kind of like King who?
King Midas.
King Midas. Criddle, tell us about it.
It touches stuff and it turns to gold.
Was Criddle the only one that knew that? We've had to have heard of King Midas before, right? Then his daughter runs up and he grabs her and she... Isn't that pretty much the story? Something like that, right? What'd you say, Richards?
I thought you were going to say King Kong.
Yeah, so did I. I was like, King Kong. I don't know. Talking about radio.
No, King Midas, right? Because, I mean, let's face it, they spent hundreds of years trying to turn everything into what? Into gold, right? Talked about that in the acids video. Now, who in here is smart enough to figure out what this is? No, I'm serious. Iverson, you're pretty smart, right? Yeah, I'm talking to you. Sydney? No idea. Anybody got an idea? Garrett, think you got it?
Thorium?
Thorium?
Yeah.
So thorium, is that TH?
Yeah.
Thorium what?
231.
Thorium 231
Yeah.
and
90.
90. Well, what you got there? What you got there, Deb?
Two of them. It's just like
Oh, so it wasn't that complicated. Little subtraction going on there. Problem is, he's wrong.
two of them.
Now, why is he wrong?
Because there's two.
I'm giving off 2 alpha particles, right? Through 2 alpha emission. So, he was on the right track and he had the best idea and pretty much gave it away for everybody else. So who knows what it really is? Radium? Radium what? How do I know what symbol to go to? Yeah, I'm just going to subtract the numbers, right? Well, this is going to be 92 minus 4, so it's got to be 88. Well, what number is 88? Radium. Then how do I find my superscript or my mass number? 235 minus 8 is going to put me at 2 what? 227? That's what you would do. Mathematically, this should be easy. Should be and is, I've learned, not always the same. Yeah. Now, let's say I did this. Suppose and I understand I'm just making stuff up here. You know what I mean? I'm just making out, the elements exist, but I don't know that this always occurs. So suppose you bombard, I don't know, let's go with zinc 70 with a positron. What is produced? Okay. So I'm going to start with zinc 70, which is going to be what? No one knows what zinc is? But it is Zn 30 and 70. Now I'm bombarding it, which now means it's a what? Yeah, I'm adding it and it makes it a reactant. So I'm going to add a positron. Well, again, I wouldn't use the big B with the positive on it because that doesn't allow me to do the math, right? So what am I going to add here? E0 negative 1, right? And that's going to produce what?
I thought it was.
Sorry, yes. I wrote down a beta particle, didn't I? Positron particle, positive 1 there. What am I going to create?
It's still gonna be zinc, right?
Is it?
Now you're gonna.
It'll be gallons.
I got to add the 1, right? So now instead of being number 30, this is going to be number 31. And that is what symbol? Ga, gallium, and 70 still, right? Now this is how you could actually make gold, couldn't I? Couldn't I take, wouldn't want to, but couldn't I take platinum? Why wouldn't I want to take platinum and bombard it with a positron and make gold?
It wouldn't stay there.
What? Yeah, platinum's worth more than gold now. Plus, I'd make it radioactive. Has anybody ever heard the term Large Hadron Collider before? Where? Yeah, no, but where did you hear it? Or me and Geddes, the only two that have ever heard of the Large Richards.
I heard it like a Bill Nye the Science Guy or something.
Yeah, probably.
Isn't it like you shoot like particles at each other?
Yeah,
Make them-
that's,
Big ring, right?
yeah.
Big ring, and they
But nobody knows where they probably really heard it the first time. Sheldon. Yeah, Sheldon. Big Bang Theory. He wins a trip to the Large Hadron Collider. Nobody's ever seen that episode?
I know.
Yeah. We all know who Sheldon is, right? Yeah, he wins a trip to the Large Hadron Collider. Instead of taking Leonard, he wants to take somebody. It's a big deal. It's funny, but that's what they do. They literally get a particle spinning really, really fast, and just like a gun, they shoot it at something. And they see what happens. Sometimes it splits it. That's called fission. Sometimes it gets absorbed by it, and they take two things and put them together. That's called fusion. All kinds of stuff going on, but that's literally how they make. All that shit at the bottom in green, that's how it's made. You take something and you shoot something at it. If it absorbs it, it creates literally something new. All those green elements are what's called synthetic. They were created in a lab using that exact thing. There's one in New Mexico. They call them particle accelerators. And they literally get that sucker spinning as fast as it can, and they shoot it at a piece of whatever they want to change and see what happens. That's how they've created all those synthetic elements. Problem is that when they do that, they're taking a radioactive particle and shooting at something. Well, what's that going to make that thing it hits? Radioactive. So does it last very long? No, most of that stuff is, I almost licked my finger so I could snap my, it's there and gone already. It just doesn't last very long. You know, francium, all the elemental, bottom left-hand corner, all the elemental francium in the world will fit on the head of a pin. Because it's radioactive. By the time they've refined it and created it, it's already decayed and turned into what? Well, it depends, but it's turned into something else. What it turns into depends on how it decays. Because if it decays by one, it's going to turn into something else. Decays by something else, it's going to turn into something completely different. Okay? So, let's try this. So, given, and I'm going to make something up, given thallium, let's say thallium 210, if you bombard it with two beta particles, you will get 3 alpha plus what? I'm going to put a blank there, plus blank. Okay? So, I'm going to do both here. I'm going to both bombard it and get something out. Okay, I'm just making stuff up here to illustrate a point. So, I'm going to start with what? I'm going to start with thallium 210, right? Which is going to be what? Okay, so I got TL, so I got thallium, and it's going to be 210 and what? 81, right? Now I'm going to bombard it with 2 beta particles. So I'm going to add 2, what's a beta particle? E0 negative 1, right? And that's going to produce something, we don't know what, plus what? 3 alpha particles with it, which is 3 He 4 and 2. Now, 10 hands for who can figure out what goes right there. 1, 2, 3, 4. People, this should be easy. 5. 6. 7. 8. Dos más. 9. Uno más. 10. Alrighty, so who was 5? What do you got for me, Celeste?
I have gold. So it's 79 on the subscript. And then 210 on this.
210 on the superscript. She right? No? So this works, right? Okay, but what's wrong? She didn't take into account this, right? Because if I'm being bombarded and I'm giving that off, this is like a math problem doing a little bit of what here? Starts with an A. Algebra. Huh. Imagine that. Chemistry teacher teaching math. Oh, wait. I teach math as well. So, what does this have to be? 1 what? 198. Where are you getting 198 from, whoever said that?
210 minus 12.
Yeah, so the 210 was right, but then I got to minus off that 12. So what I used to do when I first started teaching this, and I guess we could still do it, is I would literally go through and do the math and write them down up here. So I know that my superscript's got to end up being 210, right? My subscript has to end up being 79, right? Correct? Well, what does this give me over here? 12. This gives me 6. And then to get that, I'm only going to take that and subtract that, and it's going to give me 198, right? I'm going to take that, and I'm going to subtract that, and it's going to give me 73, right? Then all I've got to do is look at the thingy. You mean the periodic table? I'm going to look up number 73, and it's going to be TA. Just like that. That's how you do that problem. Okay? Let's do it again. Okay? So let's say I take, I don't know. Let's say I take terbium. So I said given terbium, and let's go terbium 160. Okay, if you bombard it with 2 alpha particles, you will get let's go with 5 positrons. Oh, I put that T in there. 5 positrons. 3 gamma rays plus what? Okay. So I'm going to start with terbium 160. I'm going to bombard it with 2 alpha particles. I'm going to get 5 positrons, 3 gamma rays, and what? I want the full equation, and I want 10 hands. Boom, good job. 2. Fish, was that your hand?
No.
No? Okay, we're at 2. I need 8 more. 3, 4 now. Oh, I see how it is. Five. Did I have a 6? Or am I still at 5? Must still be at 5. Six, 7, 8, dos más, 9, uno más. Ten. There we go. All righty. Who was 4? All righty, Fish. What do you got?
Alright, I said like W and then superscript 168 and then subscript 74 was the blank.
No. I want the whole equation.
Okay, so
So I'm going to start with TB.
160 in the superscript, 65 in the subscript,
Okay, is she good there? Okay, and then I'm going to add 2.
and then
HE 4 and 2s, right? And that's going to produce 5 positrons, which is going to give me 5 what?
0 B,
EE
0 negative 2,
positive 1 plus
3,
3 gamma rays, which really these don't what? They don't matter. They're zeros, right? Okay, plus, so what goes in my blank?
I said
W,
168,
168, 74. Anybody get W, 168, and 74? Just one person. Well, let's look at it. What do I have on the left? I got 168 as my superscript. I have 69 as my subscript, right? Okay. Now, right now I've got 0 and 0 as my superscripts, right? So the 168 works, correct? But I have plus 5 right here, don't I? There's nothing there. Well, 69 plus 5 has got to be, that is 74, or no, subtract 5, which is going to give me 64, which now is no longer W, right? So 64 is going to be what? GD? Is that gadolinium?
Wait, why
Yeah.
is it subtracted?
Well, because they have to balance, right? This yield sign is a lot like an equal sign, right? These numbers must match those numbers, right? I'll give you some ghost knuckles. Did you get it right?
Yeah.
There you go. Good job, Iverson. Yeah. Is that making any sense?
Yeah.
Yo,
So
Richards.
the positron doesn't have mass, right?
Yes.
It has no protons.
No protons.
So why does it change the element that you get if it doesn't add any protons?
Okay, so I used to go into this whole big explanation of how this works, but what it is a positron, and let me show you what and I used to actually teach this, but it got to where all I ended up doing was clouding people's minds with stuff that they weren't going to be tested on. Right here, Richards. A positron happens when a proton ejects its charge right here, leaving it becoming a neutron. So my mass doesn't change, my charge just changes.
So it's like a proton.
It's a
with-
proton that turns into a neutron and basically shoots out its charge. Okay.
So it still has the mass of the proton.
Exactly. Because the proton and neutron are pretty much, they're not exactly, but their mass is pretty much the same thing. The difference is negligible. Okay? And it's funny because I used to teach each one and how they worked and why it happened, and then I realized my kids don't care. They want to know what it is and how to use it. Am I wrong? No. Okay? Alrighty. Time is yours. Use it wisely. Got a half an hour. I would get going on those Learn Smarts that are now check it, but they should be open.